Engineers at NASA's Jet Propulsion Lab recently announced a breakthrough in rotor technology, and you are right to be interested because this directly impacts the future of autonomous flight. The real stakes here are not just about flying faster, but about whether we can ever build heavy-lift drones that operate reliably in extreme environments. By the end of this explanation, you will understand why this aerodynamic optimization solves the power problem, but hits a hard wall when it comes to structural integrity and control complexity. Recent flight demonstrations from the Jet Propulsion Lab regarding Venusian aerobots have validated buoyancy-based lift as a viable strategy for extreme environments. This success is impressive, yet it underscores a critical limitation of our current rotor technology when we try to scale it up for heavy-lift autonomous missions. The core issue lies in the distinction between energy efficiency and structural survivability. The so-called dumb rotor design excels in energy efficiency for lightweight, slow-moving platforms like the Ingenuity helicopter or the Venus Aerobot. However, it fundamentally fails to address the structural load and control complexity required for heavy lift, vertical takeoff, and landing. The engineering trade-off is stark. Achieving the necessary lift-to-weight ratio in thin atmospheres or with heavy payloads demands rotor speeds and blade loads that exceed current material fatigue limits. As we increase the mass of the vehicle, the quadratic relationship between rotor speed and power consumption creates a hard ceiling. The system becomes too heavy to fly efficiently, and the control complexity for stabilizing such rotors autonomously becomes intractable without active, heavy control surfaces that defeat the weight savings. This suggests that while the dumb rotor is optimized for specific low-mass missions, it cannot scale to heavy-lift applications without a paradigm shift in structural materials or control algorithms. Now consider the specific breakthrough from the Jet Propulsion Lab. Their variable geometry rotor achieves efficiency gains by decoupling blade pitch from rotational speed. This allows the blades to adjust their angle dynamically to maintain optimal aerodynamic performance across different flight regimes. In steady-state flight, this design reduces power consumption by 15 to 20% compared to fixed-pitch rotors. This is a significant improvement for missions where every watt of energy is precious, such as long-duration exploration on Venus or Mars. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. However, here is the thing that the headlines often miss. This efficiency comes at the cost of introducing a control loop latency that exceeds the bandwidth required for stabilizing heavy-lift vertical takeoff and landing in turbulent atmospheric conditions. The mechanism that allows the blades to change shape requires actuators and sensors that introduce a delay. In a light, slow-moving drone, this delay is negligible. But as the vehicle gets heavier and the forces acting on it increase, the system becomes unstable. The control loop cannot react fast enough to correct for turbulence or sudden shifts in load, forcing a return to fixed-pitch dumb rotors for scalability. Let us look deeper into the structural implications. The structural load analysis reveals that while variable geometry designs reduce power consumption, they introduce nonlinear fatigue failure modes at the actuation joints. These joints are the weak points where the moving parts connect to the blade structure. As vehicle mass increases, the stress on these joints scales exponentially. The forces generated by the torque and shear forces during takeoff and landing create stress concentrations that current composite materials cannot withstand indefinitely. This makes them unsuitable for the heavy lift regime without prohibitive weight penalties. The very mechanisms that provide efficiency become the points of failure when the load becomes too great. This brings us to the concept of autonomous scaling. Autonomous scaling fails with complex rotors because the control algorithm complexity grows combinatorially with degrees of freedom. A fixed-pitch rotor has a single degree of freedom, the rotational speed. A variable geometry rotor adds the degree of freedom for blade pitch, which must be controlled in real time for each blade segment. As you add more segments to increase efficiency, the number of control variables explodes. This creates a dumb rotor ceiling, where the computational cost of real-time flight control outweighs the marginal efficiency gains for heavy payloads. The computer required to manage these variables would be too heavy to carry, creating a paradox where the system designed to be efficient becomes too heavy to fly. Production trade-offs further highlight this limitation. The reliability of the actuation mechanisms in variable geometry rotors drops below 99.9% availability after 500 flight hours under high-load conditions. In contrast, simple fixed-pitch rotors maintain structural integrity for decades. This makes the latter the only viable architecture for long-duration, heavy-lift missions. When you are designing a system intended to operate for years in an environment where maintenance is impossible, you cannot rely on complex moving parts that are prone to wear and fatigue. The breakthrough is fundamentally an aerodynamic optimization rather than a structural one. The system solves the how much power problem, but fails the how to survive the torque and shear forces problem. This leaves the fundamental physics of heavy-lift vertical takeoff and landing unchanged. We are still bound by the same laws of physics that dictate that as you scale up, the square-cube law works against you. The atmosphere exerts forces that grow faster than the structural strength of the materials we can currently manufacture. This leaves us with a primary knowledge gap. We must determine whether novel composite materials or distributed electric propulsion can bridge the gap between current rotor efficiency and the structural integrity needed for autonomous heavy lift, or if the physics of the atmosphere strictly enforces the current scaling limits. Until we solve the structural load issue, the dumb rotor will remain the ceiling for autonomous scaling. We can make the rotors smarter, but we cannot make them lighter without changing the materials themselves. The path forward requires a shift from optimizing aerodynamics to engineering new materials that can withstand the extreme loads of heavy-lift flight. The lesson here is that a breakthrough in one domain does not automatically solve the problems in another. Just because we can fly more efficiently does not mean we can carry more weight. The engineering community must look beyond the headlines of power savings and focus on the hard reality of structural limits. Only by addressing the fatigue and control latency issues can we hope to build the heavy-lift drones that will define the next era of exploration. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.